recording. So here we go. So we know that we will be available for other people to watch. So I'm just going to pick up where we left off on Monday. And I've got this problem right here that we were working on whenever the bell rang and cut me off. I'm sorry. I was not paying attention to my timer. So anyway, we were on this problem. We had worked using the summation of a geometric sequence. We had gotten down here to this answer, and I just wanted to reconfirm what was going on. My calculator was giving me this really weird answer, -2.7 times 10 to the 10th. And I just want to make sure everybody knows what that means. That's in scientific notation, right? So whenever you see that on your calculator, it'll say like E, and then it'll have an exponent like e to the 10th, e to the 5th, e to the whatever. That tells you that they moved it that many spaces. So when it's 2.7, that means the decimal was right here between this. They really have already moved this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. So that's how I got this really huge answer and knew that it was actually 27 billion, whatever. So you're not going to have to worry about that on our exams because I'm not going to give you questions that are that huge. And hopefully I double check all my answers to make sure they're not that huge whenever we work them out. That was 18 terms, and it was on something that was a geometric, so that's multiplied. So that gets really big really fast. So we will try to avoid those in the future, really big ones. But you might see something like that on a homework or something, so I just want you to know. All right. So I feel like we're done with that section. I haven't gone into Math Excel, but I'll make sure that everything's updated on due dates and stuff like that. But you should be able to do like 8.2 and 8.3 now. I think that's the homework that's on there. So we'll make sure. All right. So moving on. Our current content, where we should be, we're actually going to hopefully cover 2 sections today. One is quadratics. But I don't intend to spend too terribly much time on quadratics. Oops, let me focus that a little, maybe. Maybe that's better. I don't know. I don't plan to spend too much time on quadratics because we've already talked about them, right? We talked about how we take anything that's a quadratic. It starts out looking like y equals ax squared plus bx plus c. Okay, that's the general form. And we've talked about how the parent function of that, the original, is just y equals x squared, right? So that's the original. When we say parent, we mean like the original. Okay, so that's what that comes from. And we know that these particular graphs look like a parabola. Y equals x squared. They're centered at the origin, 0, 0. That's an even function, so it should be symmetric around the y-axis, right? And for right now, it remains an even function, but we know that if I add and subtract weird stuff to it, like if I had something like this, y equals 3x squared plus 5x minus 9, when I look at that, I've got an even exponent, I've got an odd exponent, because this is x to the first, right? And I've got an even, because that's x to the 0. So this has an even, an odd, and an even, so that would be neither even nor odd, which means that if I went to go graph this particular function, it's still related back to the quadratic. I'm going to graph him real fast. He's still related back to the quadratic. He still has this parent function, but because I added this 5x to the first guy in there, why is this not focusing there? Because I added that 5x to the first guy in there, it basically is going to move it off of the symmetry. So it's not going to be y-axis symmetric anymore. It's going to be neither. So let me graph this guy. Y equals, I'm going to say 3x to the second, okay, plus 5x and the minus 9. And whenever I go to graph him, oops, I've got an old plot on there. Hang on a second, let me turn that off. Okay, here we go. Whenever I go to graph him, I see he's still this nice pretty parabola, but see how he's not centered on the y-axis anymore? He still has something we call an axis of symmetry, meaning I can still split him right up the middle and he would be symmetric on both sides. Let me zoom fit him so he looks better on my, there we go. Okay, maybe that's better. But I can tell there's more of the parabola over here than there is on the right-hand side of the y-axis. So he is not even anymore. Okay, we've moved him. But he still has an axis of symmetry. It goes right through his vertex. So what we need to pick up is this vertex stuff. That's the only thing about quadratics we haven't really talked about. And I mentioned, you know, we pick this guy up when we start shifting him around left, right, all that kind of stuff. We know how to do those transformations, and the vertex, that turning point there, it just moves and then we take the rest of the parabola with it, right? So it's really important with parabolas that we be able to find where that vertex is. So that's the turning point on a parabola. That's what a vertex is. Okay, and in particular, we talk about parabolas, but then later we'll talk about turning points on cubics and stuff like that. That's actually the next section that I'm hoping to get into today, is some stuff about just regular old polynomials that aren't just quadratics. But we need to be able to find that vertex point. Now, if I had something that was in the form, like what we had when we were doing transformations, let me grab one real quick. Y equals x minus 2 squared plus 1. Okay, that one looks really familiar, right? Okay, this is in what we call standard form. And the reason why is because we know what these shifts are doing for us. This moved us to the minus 2 on the inside. It's a horizontal shift. And because it's inside the parentheses, it's opposite of what I feel like it should be doing. It's not left, it's right. Does everybody agree? Horizontal shift right 2. Okay. And then this one on the outside, that's on the outside, so it's a vertical shift. And it's up 1, right? It's actually the direction you think it'll go. So if I was graphing that particular guy, come back to my other guy, y equals, okay. Let me put him in there. It's parentheses x minus 2 squared, and then plus 1. We know that this should shift to the right 2 and up 1. So it's unfortunately not going to be even anymore because it's moved it again off the y-axis, but it still has that same original parent function, right? And we see, look, the vertex is right here. It moved to the right 2 and up 1. Okay, so that's exactly what we think is happening here. So the nice part about standard form is that we can find that vertex by looking on the inside. Okay, so we see it went right 2, that's a positive 2, and it went up 1, that's a positive 1. So the vertex, we always take the opposite of the inside, because again, that's horizontal. Okay. So right 2, up 1. Opposite of the inside, the same as the outside. So in your book, what you would see is that they give you something that's called the standard form of a line, of a parabola, sorry, not a line. And it looks like y equals, and you have this stuff on the inside. You might have an A on the outside. I'll stick him out there so we can see him. I'm looking for the actual formula. A parentheses x minus h squared plus k, where my vertex is always h comma k. So I just pull this value, change the sign. Oh, sorry. Thank you. So this guy where the vertex is h comma k, I just pull this guy out, make him change signs because he's on the inside. And then I pull the k out, whatever that constant number is at the back, and just put him right there. Okay, so that's what the vertex looks like in the standard form. And if it's already set up like that, it's already in the parentheses, we're already set up to do transformations like that. It's actually pretty simple to go in and find the vertex. That one's not the bad one. Okay, so we just look inside and go, oh, that's it. So if I gave you y equals, here's an example. Y equals, let's do 3 parentheses, x plus 5 squared minus 6, okay, and said, find the vertex. Then all you're going to do is you're going to go into the parentheses. You're going to see that it's a plus 5. So I know we're shifting at 5, but we're not going right. We're going left. So my vertex is going to land on -5 because I went left, right? Always leaving from the 0, 0 guy. So it goes left 5 is -5. And then the up and down is just exactly what it looks like, right? This went down 6. So my y value for my vertex is going to be -6. So again, not too difficult, I hope, to pull out that vertex. That's not the one that I worry about. Okay. The one that I worry about with these is whenever it was given in the general form. So I'm going to go back to this guy that we had up here. Okay. Whenever I'm given these parabolas and they're in the general form, parabola in general form, it's not already rearranged for me. I can't do transformations off of it very easily. Now, there is a process called completing the square, and if you wanted to do that, and sometimes I can show you that, that's not it's a little bit of a process. It's probably about a 6 or 7 step process that you can complete the square here and you can put it into the standard form. Okay, so you get the stuff by itself, you factor, and so on and so forth. But that is quite a process, and we don't want to have to do that every single time that we want to figure this out. So I've got one right here. Y equals -x minus 2x plus 1. That's my example. We're going to do this one first because it's got an even guy in the middle. I'm sorry, 2x squared. I'm sorry. -x squared minus 2x plus 1. Sorry, I left off my exponent. Okay. So when I look at this, let me pull this back down. The general form, what we need to know is what are the A's, the B's, and the C's. So we haven't messed with that before, but when I look at this off to the side, I can write up my A equals, and it's going to be whatever the coefficient is that goes in front of x squared. Well, this is a negative and there's no number there, but I know it's supposed to be a what? -1, right? Like you could write it in there if you wanted to. There's a -1 there. We don't normally write it because we're just lazy and we don't want to write the ones out there if we don't have to. But my A is -1. Okay. And then what about my B? B is the coefficient that goes with your x term, right? So it's a -2. You're going to have to be able to see these and go, oh, there's my A, there's my B, there's my C. And the C is the constant that's just sitting out there by itself, right? So C kind of means constant here. So it's a 1. So C equals 1. Okay. If I can identify the A, the B, the C, then I can use a little formula. And like on the last test, you're not going to have to memorize necessarily. You're just going to have to be able to recognize it. You see it in there and you work with it. So for vertex, whenever we're in this general form, what I'm going to do is I'm going to find my x value of the vertex by using x equals negative b over 2a. Okay, and that's just a given. It's actually comes from part of the quadratic formula, if you know that guy. Okay, but we're not going to worry about that right now. We just are going to look at it and go, okay, I'm looking for negative b over 2a. That's going to be the x value of my vertex. So if I've got these values already written off to the side, then I ought to be able to come back in and say, okay, well, that means that x equals negative. My b is a negative 2. So there's a negative in the formula, and then I've got a b of negative 2. So I'm going to put parentheses just to make sure. So it's negative b over 2 is in the formula, and then times the a. Well, I'm going to put parentheses again because my a is times negative 1, right? Okay, my a was a negative 1, so I stick him in there, okay? So now it's just a matter of messing with my positives and my negatives. A negative negative 2 is going to be a positive 2. And on bottom, a 2 times a negative 1 is going to be a negative 2. Okay. And then thankfully this one reduces. They don't always reduce. So we'll see that in a second. Okay. But this becomes a negative 1. So I've got the x value of my vertex. Okay. So I'm going to have my vertex. I'm going to skip a tiny bit of space here. We'll find out what the y value is. We'll get that in a second. But my vertex is going to look like negative 1 for the x value, and we'll find the y value. Okay. Okay. So how do I find a y value? I take my x value and I plug it into the formula, right? So the original equation. So this was the negative x squared minus 2x plus 1. I'm just going to plug in that negative 1. So I'm going to copy. I've got a negative from the original equation. For my x, I'm going to plug in negative 1. That's squared. Minus 2 from the original equation times the x. Again, I'm using x equals negative 1. And then plus a 1 that's in the equation. And if you want to do like we did whenever we were doing the substitution stuff and just like put parentheses, come back in and plug in your negative 1, you can. Okay. The idea here is I'm only using the coefficients. I'm not using any x's because when I finish, I should have a value here and a value here, just a number value. I don't want any x's in my vertex, right? So when I'm done, hopefully I just get a number coming out. So let's look. Inside of these parentheses, I've got negative 1 squared. A negative times a negative is going to be a positive. So that's going to be a 1. But then I know there's a negative out in front. So negative 1 for that first little bit. Then I've got a negative 2 times a negative 1. That's a positive 2. And then I've got a positive 1. So I've got negative 1 plus 3. So 2. That's my y value. And I'm going to stick it right there in the vertex. So I've got a negative 1 comma 2 for my vertex. Okay. And that's how I can find the vertex without having to rearrange this guy and look like it's in standard form. Okay, so I just look at it, I go, okay, great. I find my x value, then I plug that x value back in. So find my x value, here it was, x value, that's step 1 of the vertex by using this. And then step 2 was plug the x value into your equation to get the y value of the vertex. So negative b over 2a gives me my x, then plug that guy back into the original equation and get my y. That's my vertex. All right. And that's really the heavy duty part of this. I'm going to do the one that I started with at the beginning of this, just so that we can see what if it's not nice and pretty. And then we'll talk after that. Is everybody okay? All right. So the one I had earlier, I gave as an example, was right here. I said, what if y equals 3x squared plus 5x 3x squared plus 5x minus 9. Okay. And we're going to find the vertex. So when I start looking at this one, immediately I notice that, hey, when I take negative b over 2a here, step 1 is the x value using negative b over 2a for my x. I'm going to see that the b here, I'm going to come off to the side. My a is a 3. That's okay. The b here is a 5. Okay. And when I do that, that's not going to be divisible by 2. Okay. So I'm going to get a really ugly number here. And then the c is still negative 9. We don't need him right now. We'll need him later, like if we were using the quadratic formula or something like that. But so when I come to do this math here, negative b, negative, it's a 5, right? So negative 5 over 2 times a, that's 2 times 3, right? This answer is negative 5/6, which is not a pretty value for me, okay? And sometimes that happens. So my vertex is going to be negative 5/6 for the x value. Let's stick it right here, vertex. Negative 5/6. And then to find the y value, we have to plug that back in, right? So it's not always going to be just as lovely as that first example that we had. That one worked out very nice and pretty, but this one's not going to be so great. So plugging in, I'm going to plug in negative 5/6. Okay, go back to my original. It's 3 times whatever my x is squared plus 5 times the x minus the 9. I'm going to use this negative 5/6 guy for my x because that's what I want to plug back in, right? This is step 2. Plug it back in. All right. So now I'm looking at this going, okay, I got to do this stuff in the parentheses. It's not going to be pretty, but it's going to be doable. When I square that guy, negative 5 on top times negative 5 is a positive 25. And on bottom, it's a 6 times a 6 is a 36. Okay, so you square the top, you square the bottom. Okay, it makes it positive, which is kind of nice. Okay, but now I'm going to have, so like for instance, this is a whole number times a fraction. I'm going to write 3 over 1 so that it looks like a fraction because I know whenever I multiply fractions, fraction times a fraction and straight across the top, straight across the bottom. Okay. And same thing for the 5. I'm going to make it 5 over 1 and this negative 5/6. And then I've got this minus 9 that's just kind of hanging out in the back. So I'm going to end up with what's probably going to be a not pretty fraction. That's okay. We'll just roll with it and see what it turns out as. So y equals. I'm going to go ahead and reduce this. The 3 and the 36 are both divisible by 3. If you don't see that, you can go 3 times 25 and get the 75, and then you'll reduce at the end. But I'd rather not get that really big number if I don't have to. So 3 goes into 36 12 times. Okay. So what I get on that first fraction is a 1 times a 25 is just a 25. And a 1 times a 12 is just a 12. That's my first fraction. That's actually going to be a mixed number. If you turn it into that, it's like 2 and 1/12. Okay. I don't care if we leave it as this improper fraction. So don't feel like, oh, every time I see that, I have to make it, better. But if you want to, you can. And then here, the 5 and the 6 don't have anything in common. So I can't reduce. So I'm just going to go 5 times negative 5 on the top is negative 25. And 1 times 6 on the bottom is a 6. Okay. And I've still got this minus 9 just kind of hanging around at the back. All right. Now, I think that this is going to turn out not too horrible because when I look at this, I've got a 12 and a 6. I can get to add fractions. I need a common denominator, right? I can get that common denominator by multiplying the bottom of this fraction by 2. 6 times 2 will give me a 12. But we know whenever we multiply the bottom of a fraction by 2, we have to multiply the top of a fraction by 2. So this is going to turn into 25 over 12 minus, because I'm going to pull this negative out of this because it doesn't matter, right? 25 times 2 is 50 over 12. If you want to keep it a plus and a negative, you can do that. But I just know a plus and a negative is going to turn into a minus here. So a positive and a negative is a negative. Okay, and then the minus 9 is hanging out. Okay. Now 25 minus 50 is going to be negative 25 over 12 minus 9. Okay. And again, you can get a common denominator there if you want to. It's really 9 over 1. So if I get a common denominator, I would multiply the bottom and the top by 12. This is just kind of some arithmetic type stuff. This doesn't have anything to do with the algebra. It's just making sure we know how to add and subtract fractions, multiply fractions, so on and so forth. So let's see, 9 times 12, what's that? 108, I think, over 12. Please check me. I got a calculator. I'll double check. 9 times 12 is, oh, really? 108. Good. Okay. So now I've got a negative and a negative. They're both negative. So I'm going to add them. It'll be negative. What's 25 and 8? Oh, I can't do this in my head today. Sorry. 133 over 12. So there we go. That's my y value. It's not pretty. Okay. They don't look like they're both divisible by anything. 133 is not divisible by 3, not divisible by 2. So I think that's just it. If you want to make this into a mixed number, you can, like it would be what? Negative, is that 11? Maybe negative 11 and something. You can do that. But to me, again, that's just another place where I can make a mistake, and I'm not worried about improper fractions. If you want to move it, change it, you can, but there we go. Okay. So if that even number is not divisible by whatever goes on bottom, you're going to end up with some kind of ugly fraction probably. I know. No pretty. All right. The last thing in this section before I start talking about polynomials is that you might have a word problem going on with this. So think about it like this. If I were to throw a ball, it would start here at the ground level. It would go up. It would arc over, and whenever it comes down, it would stop here, okay? The idea behind those word problems, all of those word problems, is that when you throw a ball or kick a ball or shoot an arrow or anything like that, that it kind of has a parabola look to it. Okay. And they'll talk to you about things like maximums. Okay. Well, if my parabola is an upside down parabola, this means like I had a negative out in the front, right? So this guy right here would be my maximum. Okay, so I can find that by finding the vertex. Okay, so that's why we concentrate on finding the vertex. The vertex can be your maximum or it can be my minimum. Now for a minimum, it would have to look like that, right? It would have to be what we consider a normal parabola. And then the vertex here would be the lowest point, right? So when you start reading through word problems and stuff, realize if they're talking about maximums or minimums, then they're talking almost always about the vertex. The other thing is if I was standing on the ground here throwing this ball, okay, then when I started that, my time would start at 0, right? And my height would start at 0. So sometimes they'll want to be like, oh, when's the ball going to hit the ground, right? So you're looking for where the height would be 0 again, right? Because it would go up and then it would come down and your height would be 0 again. So those end up being my x-intercepts. right? Because if this is like my x-axis, it's where it started, it's at 0, and the height is at 0, the y value. And when it ends, it's at 0. So those would be like my x-intercepts. So they're gonna ask you to like use a parabola and actually do some kind of application stuff with it. That's what's going on there. Okay. So I want to dive into polynomials just a little bit. I know I don't have but about 10 minutes left on my time clock, dang it. But I want us to at least look at that and see what's going on. A polynomial so the thing nomial normally means like a binomial would be 2 terms, a trinomial would be 3 terms, that kind of thing. Poly means multiple terms is what we're talking about. And we need to be able to kind of look at an equation or a graph or something like that and say, hey, is this thing really a polynomial? So some things are not polynomials. For instance, if I gave you y equals the absolute value of x, we know that this graph looks like this, right? It's a V, okay? And the important part about this graph for our purposes, for knowing if it's a polynomial or not, is looking at that sharp corner, okay? So this is not a polynomial. And the reason why is because it has a sharp corner. Okay. So this is like my counter example. Those are things that are not going to be polynomials. But things that are going to be polynomials are things like y equals 3x squared plus 5x minus 9. Okay, that's why I'm talking about that guy, because he's a parabola, he's a quadratic, but he's also a polynomial. Things like y equals 5x cubed minus 4x plus 1. Okay, that's a polynomial. Okay, and there are ways for me to tell just by looking at the equations what are polynomials and what are not. So these are yes. Yes. Okay, so here's how I know. First of all, I look if I have the equation, then what I know is I can have any exponent that I want as long as it is an integer. Okay, so the exponents, I'm sorry, not an integer. What do I need? Whole number. Yeah, whole number. Exponents are whole numbers. Let's say it that way. Okay. So like I can have x to the 25th. That's fine. No problem. I can have x to the 0 because all of these constant numbers really technically have x to the 0 in the back of them, right? So whole numbers are okay. What I can't have is I can't have an x in the denominator. No x in the denominator. Okay, so that would be things like y equals 3 over x, right? And that's not going to be a polynomial. That's going to be some kind of rational function. We'll talk about him later. Okay, I think in the next chapter. Okay, and what I know is that technically when things go to the bottom, there's an exponent rule that says that it's x to the -1 is my exponent right there. And I think there's a basic review in Math Excel that talks about exponent rules. So these are not a polynomial. So I can't have an x in the bottom, so no negatives, and I can't have a fraction in the exponents. Okay, so that would be things like y equals the square root of x, which is the same as x to the 1/2. Okay, fraction exponent. Okay, so when I see those square roots and stuff, I think, oh no, that's not a polynomial. Okay. So basically, I'm looking for things with whole number exponents. That's how I know by looking at the equation. But what if I'm looking at the graph? Okay, I said this guy is not. Now, technically, we could talk about his exponents, right? Because how do I get an absolute value? That would be a weird thing going on. Okay, it's not like x to the first or x to the second or x to the third. So, but if I'm looking at the graph, then I see, oh, look, I have a sharp point there. That's not okay. You can't have sharp corners. So the definition for the graph looks like this. Graphs of polynomials are, and the words we use, smooth and continuous. Okay, that's the mathiness that we use there, smooth and continuous. So for instance, when we talked about a parabola, it's smooth and continuous. It doesn't have any sharp corners. It doesn't have a spot where I've had to pick up my pencil to quit drawing it. This guy is, okay, what if it was x cubed, something like that? When I draw it, it's like this little S curve. I start and I go up and I come down and I go back up. No sharp corners. It's got these nice curvy corners, right? Where it turns, they're nice curves where I'm turning. Okay, no sharp corners. And no stopping and starting. So don't pick up your pencil, basically. If I can do that and graph the entire thing, then it's a polynomial. So these two are polynomials. No problem. Even like the W's happen in weird ways. So that's one of my favorite graphs, right? We've seen it before. So if I have a W graph, if it's this nice, smooth, continuous guy, okay, I never picked up my pencil, I never had any sharp corners, this guy is going to be a polynomial. And he's going to operate off of, it's actually, you can tell by the number of directions. So 1, 2, 3, 4. His parent is y equals x to the 4th. Okay, and I did some stuff to him. That's okay. But that, remember on the test, we had this really sharp corner one, that W. Okay, see, he's got these sharp corners. It's basically the same look, but because I've got those sharp corners, that makes it not a polynomial. And he does not have one of our nice, pretty parent functions that we know. Okay, so that's how I'm going to tell by looking at the graphs. Are they smooth and continuous? They don't have any holes or gaps. So some of the graphs that you might see might look something like this. You have a nice smooth thing going on down here, but then they had to pick up their pencil and come up here to draw a second piece. This would be like a piecewise graph. Okay, not continuous. So he's not going to be continuous, bad guy. Okay, so he's not a polynomial. And we actually have an entire chapter where we'll look at these guys, which are considered like rational functions. All right. So I think I'm just about out of time. I'm going to try to stop before your bell. I think you can do the 3.1 homework, which is quadratics, but we're not quite done with polynomials, which is 3.2. So hold off on that. Okay. You ladies got any questions? All right. Is that the bell? You're probably close. All right. If you don't have any questions, I'll see you next time. Actually, you'll see my video, I guess. Take care.